Thank you very much for the invitation. It's wonderful to be here again. It's a great program. I watched quite a few videos of the talks that were presented here before. And in particular, actually, one of the talks was by my co-author, Thomas Berggren, on this work. So some of you may be bored to hear about it again. I'll say something about my motivation a little later. Unfortunately, I couldn't have come to the Dimer workshop that was here earlier. Teaching is hard, as we all know. In fact, it's quite satisfying. My students are writing the exam as we speak, so it's doubly pleasant to be here during this time. Right, so this workshop is on vertex models, right? And I am not going to talk about vertex models per se. And there is a mathematical and a non-mathematical reason for that. So mathematical reason is that I wish I could talk about vertex models and show you something similar. I think what I'll talk about should have a life within the vertex model world. And some simple cases of that do have that life. So I'm hoping that whatever you'll see will get embedded into the larger world of vertex models of, let's say, Jan Baxter solvable vertex models in some way. And the last mathematical reason is that I unfortunately I cannot come to Philippe's conference next month, and his work on dimers was inspiring to me, so I wanted to talk about the dimers in front of him, so you cannot sleep now, Philippe. All right, so with that, what am I talking about? So I'm talking about dimer models. I suspect they don't need an introduction in this audience, but still, in one word, one is looking at a graph and at different ways to cover the graph by edges in such a way that every vertex is covered exactly once. It's called perfect matching in combinatorics, or a dimer cover in physics. And so one wants to put a probability measure on them in some way. If the graph is finite, the easiest way is to take the uniform measure, but there are other ways as well. And so then the question is, what does a typical dimer cover look like? So that the dimers, as a subject, I guess, go back a long time to chemistry literature. At least this is the earliest reference I was able to trace, somewhere in the 30s, actually probably the same year when the six vertex model was first introduced, also in chemistry, but by a different person. So the dimer models were extensively studied in the 60s, I think largely because of connection to the two-dimensional Ising model, but most notably, they were solved in the sense of evaluating partition functions for planar graphs in terms of phi-fins and determinants. Now then, one thing I want to note is that in 1980s, a group of physicists, Nienhuis, Hilhurst, and Blote, so they suggested that dimer models have relevance for modeling a physical phenomenon that can actually be observed with, well, not quite naked eyes, but with an actual photograph. So the photographs are on the right. These are actual pictures of helium near absolute zero. And you can see that it's very cold, like here and here. There are crystals with completely flat faces. Well, whether they're completely flat or not, on the atomic level, the picture is not going to show, but pretty flat. And then when the temperature rises, so you probably cannot read, but here the difference is roughly 1 Kelvin. So rises maybe not so much, but still rises. What happens is that these flat faces, they start to curve and they start to fluctuate. They become rough. Instead of being very smooth, they become rougher. So this is known as the roughening transition in physics. I am actually not sure there are now physicists studying that. I was not able to find almost any contemporary papers in physics, but there was time when people cared. And then since early 1990s, mathematicians picked it up, and so Rick in particular played a big role in development of the subject. And I'll be more on the mathematical side, I guess, although I'll try to make the connection to this picture at some point. Okay, so that was very general, so I'll talk about very specific situation. I'll only talk about the square lattice, so my graph will be a piece of the square lattice, and moreover, the domain will only be a square. So there are two different ways to place, or not many different ways to place a square on the square lattice, but there are two maybe easiest ones. One, you just place it with sides parallel to the grid lines, and the other one, you place it at 45 degrees. So then you get the square, which is here on the, which is here on the left, the plane square, so to say, and then the rotated square, which was named the Aztec diamond by Jim Propp, and that will be my main hero for most of the lecture. So this is an example of a dimer covering of the Aztec diamond. And there is a useful tool to look at these dimer coverings. One can associate to each edge a little domino, so a rectangle, 2x1 rectangle around that edge, and then cover the domain by these rectangles, as here. And then one can also color them in 4 colors in the following fashion. So one first notices that this graph is bipartite. So the theory of bipartite graphs is very different from non-bipartite graphs. And then the horizontal edges will come in 2 sorts. They will either join white on the left and right and black on the right, or the other way around. And so you can color them into different colors, and same thing for vertical ones. So you get 4 different colors. This is the coloring here. And then if you do it for a uniformly random dimer cover of this domain and this domain, you get these 2 pictures. And they are quite different, as you can see. So boundary conditions matter. Here you get something very uniform. Here you get something very non-uniform. All right. So then there is one more tool that is useful before one goes into any kind of study. So that tool is passing to a 3-dimensional picture rather than the planar one. And so I'll actually do the, instead of trying to walk you through this picture, I'll try to show the 3-dimensional situation. So these are 4 dimers of 4 different colors. And so one can lift them into space according to their color in separate ways. I hope you can see this in 3 dimensions, that what used to be flat now becomes 3-dimensional. You get these pieces. And the reason that you want to make these pieces is that if you start with a cover by dominoes of the Aztec diamond, and then you replace each of the dominoes by this piece, then altogether they will form a plot of a continuous function. Okay, no, not just continuous, Lipschitz function. Very nice function called the height function. And it's just easier and more pleasant to talk in terms of the height function than in terms of the actual cover. Well, for some questions anyway. So that's this is a one-to-one correspondence. If one can draw the height function satisfying certain conditions, then there is an associated dimer cover. And so this is a picture of the Aztec 100 on 100, I think, with the uniform measure, sample of the uniform measure. And then if you do the same three-dimensional thing, then you're going to see that sample, the typical thing, will approach the some limit surface, which is called the limit shape. And and finding it was one of the important results in the theory. Now, in the middle here, maybe I won't show the simulation. So this is the picture of what one gets when one starts with the square with the sides parallel to the grid. I complemented by the 4 corners just to make it sort of similar boundary conditions in this one. And so if one does that, then again, if you go in 3 dimensions, then you see a very different picture. You'll get something almost completely flat here in the middle. But not quite completely flat. You'll still see fluctuations over there. So just remember these fluctuations because there will be other flat things later on. And so then one can compare this flat to that flat. All right, any questions so far? Yeah.
How do you make it flat in the middle? Did you do that
So I don't make it. What I do is I take a square like that, and then I look at the tiling, and then when I lift it up by my recipe of turning dominoes into 3-dimensional shapes, what will happen is that, so the domain will force the height function to be 0 on the boundary, or very close to 0.
Oh, you
and then in the
fix
middle,
it by the boundary condition.
You fix it, so the domain actually fixes the boundary condition. Yeah, the shape of the domain prescribes the boundary condition. Right. Anything else? Sorry for being boring. I'm sure that's pretty clear to almost all of you. All right, so the uniform measure on the Aztec diamond has been studied. This is probably the most studied diamond model ever. Everything, or maybe almost everything, is known about it. Okay, many people contributed starting from early 90s, and so this is a list of some of the results. So let me just go quickly through them. The total number of tilings for the Aztec is very nice. It's a clean power of 2. There is an exact sampling algorithm known as shuffling, which only involves flipping independent coins. So that's wonderful because you can make the computer sample this picture very quickly for large sizes. So when you look at the picture, you see that there is a curve that separates the frozen parts, the single color parts from the chaotic ones. And so this approach is a circle that's known as the Arctic circle, one of the earliest results on the Aztec. Actually, probably the number of times. I don't know what was the earliest. Maybe Rick knows. But what was the earliest result on the Aztec, Rick?
Well, the EKLP paper, 92, yeah.
This one.
Yeah. And the Jokish Prop Shore did the Arctic circle.
Yeah, they did the Arctic circle. That's later. Okay, so this one had the numbers, right? Yeah. Okay, and then one can go into the bulk of the picture, and then one can look at the behavior of the dimers locally. Well, here it's boring where the color is single because you'll just see frozen thing. But if you go in the middle, then there will be some randomness, and one can understand that randomness as a 2-dimensional family of measures. They're known as translation invariant Gibbs measures. So they were classified, they're known, they were proven to arise inside the Aztec, and again, Rick played a big role in this development. Now then one can look at the boundary and see the fluctuations of the actual lattice picture as compared to the circle, and then one gets non-trivial scaling there, and then distributions related to random matrix theory. So that was the beginning of late 90s. Kurt Johansson in particular proved that thing, I believe. And then if you look at the fluctuations of the whole surface around of the stepped surface around the smooth surface, that will be given by the Gaussian free field. So you see, all possible, okay, not all, but many reasonable questions were answered, most of them. I mean, maybe one thing that I think hasn't been answered is that there should be SLE curves showing up in the dimer models, and I don't think this has been shown. And I think it's just asking for someone to sit down and really spend time and effort and do it. That would be quite nice, actually. Okay, now, why am I talking about dimer models if everything is known? So what I'm going to talk about is the case of the non-uniform measure. So what does it mean? So I will assign a weight to a non-trivial probability or non-trivial weight or bias to every dimer cover of the Aztec diamond. And so the bias will be the following. To get the weight of a particular matching, I will take the product of weights of the edges that participate in that cover. And the weights are going to be some arbitrarily, but periodically prescribed weights on the lattice. So I take the lattice, I pick some k by L rectangle on that lattice, I prescribe the weights arbitrarily there, positive, non-zero, and then I repeat them in both directions periodically. And so I imagine that my Aztec is going to be very large, much larger than the size of this rectangle. And so then in this product, I will get weights from different copies of that rectangle. But okay, so that's the recipe. Is it clear? Questions about what's going on? So some edges will be, some edges modulo k and L will be more likely than others. And so that seems like if you see it for the first time, that might look like a minor change. You're just deforming the microscopic rules a little bit, but I guess the whole stat physics is about microscopic changes influencing the global behavior. And so here is an example of the picture that you get by sampling periodic weights with the, I think this is a 3 by 3. Yes, this is a 3 by 3 weights. So the 3 by 3 square was fixed with some weights of the edges, and then they spread out in a periodic fashion. And then one samples with that new measure. This is what you see. So what you see when you look at it, first of all, the boundary here between monochrome and chaos is no longer a circle quite clearly. And then also in the chaotic zone, you see regions that don't quite look the same. And so more than that, if you go to a three-dimensional picture, then you see this region here will become very close to flat. So I try to zoom in, and if you want later, I have a three-dimensional model. We can zoom in, actually. If I try to do it on a laptop, I'm sure I'll screw up. I'll just waste time. So this is pretty close to flat. On the 500 by 500 sample, the difference from flat will be within 1 or 2 units. So it's really very flat. And so in particular, it's much flatter than the previous flat picture that I showed you, the tiling of the square. Actually, for the square, it's known that here the fluctuations are logarithmic, and here the fluctuations are of order 1. They stay finite as the size grows. Okay, so this is a new phenomenon.
How come there's only 1 and not 4?
Yeah, there are 4. They are correct. There are 4 regions like that. No, there is not just 1. I chose 1 in order to show that it's flat on the picture. If you turn it slightly differently, you get other ones. There are 4. So 4 happens to be 2 by 2, and so that's 3 minus 1 times 3 minus 1. So in general, there will be k minus 1 times L minus 1 regions like that. All right, so this is just to show what you can, what kind of various pictures you can get by varying these weights. So this is a 2 by 2 maybe. This is a 3 by 3, another 3 by 3, and these are probably 2 by 3, if I'm not mistaken. But you can see that they change. And the whole purpose of my talk is to try to explain what these pictures are. And why do you get these pictures? You don't get, like, can you tell what picture you get ahead of time? Okay. All right. So the main message is that you can, luckily. And complex analysis, classical complex analysis helps on the theory of Riemann surfaces, if you wish. So what you are seeing here in this picture, this was a 3x3 domain, is some sort of a projection of a Riemann surface of genus 4. So there is an algebraic curve somewhere, and I'll try to say where. Well, okay. As written, it lives within the two-dimensional complex space, so it's just the set of solutions of some algebraic equation. And so one can map it into the plane, into the two-dimensional real plane by taking complex numbers z and w satisfying the equation and taking the logs of their absolute values. So that will produce a more tangible picture. I can't quite draw this picture well. It's in 4 dimensions, but this picture can be drawn in a nice way. And actually, you can reconstruct sort of this surface here by imagining two copies of this thing over here. It's called the amoeba of this algebraic curve. So if you take two copies of this picture, imagine putting them on top of each other and gluing them on the boundary, on the same pieces of the boundary. So then when you sort of unstick them one from the other, they become, well, you have this bubble, and there will be holes inside. So you get topologically something like that. So that's so you're not losing too much information when you go from here to here, but that's because one is dealing with a special kind of curve. This is known as Harnack curves, following Michalkin's definition from about 25 years ago, I think. Okay. And then, and then there is a one-to-one map from this picture to the actual Aztec picture. And so these holes over here, these ovals, they actually map to the regions where the surface is very close to being flat. Okay. And so that describes the answer. Theoretically, I need to tell you maybe what some of the objects are. Now, there is one more picture over here. So this is the picture that is also in one-to-one correspondence with the chaotic region over the, well, not one-to-one, but some correspondence with the chaotic region over here. And so this is the picture where one takes the gradient. So there is a surface in 3 dimensions. Over here, and so at every point I can take the x derivative and the y derivative. I get two real numbers. So if I look at the domain that these numbers sweep in the plane, I'll get a square. Sorry? Question?
Did you tell us what the letter K stands for?
K, where is letter K?
First line.
This letter K? So the fundamental domain was K by L. So it's just the periods, the horizontal and the vertical period. So K is the horizontal period and L is the vertical period.
Or the period of the weight.
Of the weights, yes, of the weights. Okay. Yeah. Yeah. Oh, I don't need to. Oops, where did they go? No, so this is the same as that. So they fit without any shift next to each other. So it's fine. I don't need to do anything to fit them into this. Anything else? Right. Okay, so I was saying that if you look at the gradient or well, not really the gradient, the first two derivatives, partial derivatives, the slope, and then you look at it on the plane, then you fill the square. And then the slope of these flat regions will actually be the 4 integer points within that square. So the square will be 3 by 3. And then the 4 integer points will give you the slopes of these flat regions or smooth regions because they are really pretty smooth. And so, right. And then these for the outside four corners, these are monochrome regions that are in the very corners here. And then there are also some, we call them semi-frozen regions. They're not very visible here. So it's like this one over here. It's not quite monochrome, but there is no action going there. And so their slopes correspond to the integer points on the sides of this square. So this, if you wish, this is a manifestation of roughening phenomena. Right? So if I go back to my picture over here, there are flat pieces that are very flat. And then there are curved pieces that fluctuate much more. There is a natural question is what is, can you really do the temperature thing? So can you go down to the completely flat thing? And yeah, that one can do. So the temperature going to zero limit of this picture, of these pictures, or this picture also exists by a very lucky coincidence. This is called the tropical limit, of course, because the temperature goes to zero. Everybody knows that's what happens in the tropics. And so that's the standard terminology, and I think it's wonderful. Once you hear about that, it just sticks with you, right? And so then what will happen is that these flat regions will just fill the whole thing, and so the curved parts will shrink more. And so we think we understand how this is happening, but we haven't finished yet, so I'm not going to talk about it much, but it's there. Anything else? All right, good. So this map from here to here, I didn't tell you anything about it. Well, okay. The slide did say that this map is explicit in terms of theta functions. So theta functions, okay, the usual Jacobi theta functions are pretty nice, but theta functions associated to arbitrary Riemann surfaces are slightly less nice. In particular, computing them numerically is, okay, it's a task. Some people know how to do it, but not too many. But there are also, without even that, there are some geometric properties of that map which are sort of nice. So here is one of them. If you look at the boundary curves, so here are the boundary curves of the amoeba. So there are four holes, and then there is a boundary here. And there are also boundary curves in the Aztec. So there is an outside boundary over here, and then there are boundaries of these star-like regions in the middle. And so there is a map. The map extends to the map on the boundaries. And not only it extends to the map on the boundaries, but that map also preserves the slope of the tangent line. So, if you go around this outside region on the Aztec, so this is the Aztec here, right? So this is just the curves that bound the cows from non-cows. And so if you go along the boundary here, it's like you're going along the boundary on the amoeba, except for you're going in the opposite direction. But the direction of the tangent line stays the same. So this is color-coded to reflect that fact. From this observation, which is not too hard from the main theorem on the previous slide, what follows is that the regions that we see in the middle here, the flat ones, they are indeed star-like with four cusps in the star. And the reason being is that if you go smoothly on a closed curve in one direction, and then you try going in the other direction and preserve the tangent line, then what will happen, you'll get a discrepancy of 4 pi that you need to get rid of somehow. And so cusps are things that get rid of that discrepancy pi at a time. And so you need 4 cusps in order for this picture to exist. So in the case of the Aztec, one really has they're always with 4 cusps.
Sorry, but can you have non-generic behavior when you have different holes?
Can you have what?
Non-generic behavior with different shaped holes.
So in the non-generic behavior, the only thing that's supposed to happen here is that some of these stars can collapse. they are not going to merge into more interesting stars. That does not happen. If you want more interesting stars, you need to go to different lattices. So if you go to the hexagonal lattice, and if you look at the hexagon, then hypothetically from simulations, there is a case when you get a 6-cusp star, sometimes. Or sometimes you get 2 4-cusp stars.
Only because it's a double cover. I mean,
It's because of double cover, that's
you
right.
also do that in this, if your domain was not an Aztec diamond, but
Right.
a
Yeah.
hexagon or something.
I agree. If you create more complicated domain, you could probably do something like that on the square lattice as well. But not in the Aztec. Not in the only case we so far know how to solve by formulas. Let's put it this way. Okay. All right. So actually, I'm pretty. What do I have? I have 50 minutes. 20 left, right? Okay. So this and the next slide is supposed to explain that the limit shapes, these 3-dimensional surfaces that one looks at, are solutions to a variational problem. So there is a natural variational problem that one can set up so that if one solves it in the right class of functions, that returns the limit shape. So that's an abstract statement, a very powerful one, goes back a while. The reason for that is because one can approximate the smooth surface by little flat approximately flat parts. And for an approximately flat part, it's like trying to solve the problem in the square with the axis parallel to its sides. And there, the Fourier transform tells you how many dimer covers you get. And depending on the slope, the number will vary, and that can be used to get the variational problem happening. So that's a very nice statement. There is a list of people here who contributed, and a couple of them in the audience, right? Rick was mentioned a lot of times. Vadim is here as well. Probably no one else, but anyway. Now the problem, right, so there is some explanation to that, and so, right, so then one is reduced to the problem of maximizing a certain functional on suitable functions, right? They're mostly smooth, but sometimes they have problem with smoothness when the phases change. So that functional, the free energy or the surface tension that needs to be minimized, that functional can be computed directly from my weights. So I had the only input that I start with are the weights, right? These numbers in the K by L rectangle. So if I start with these numbers, one can produce a natural, in this setup, matrix. That's a matrix that has matrix elements corresponding to white and black vertices. And so the determinant of such a matrix slightly augmented by complex variables W and Z on the two. So if one imagines that this rectangle is drawn on a lattice, then one needs to draw 2 cycles around the torus, one in this direction, one in that direction. And so one needs to augment the weights on these 2 sides, the so-called magnetic fields. And if one keeps them arbitrary, then that will produce the partition function for the dimers on the torus with these augmented weights, which will be a polynomial. And so that's the polynomial that defined my algebraic curve. That's the polynomial that defined this object here. And then there is a natural way to extract the surface tension or the free energy. That's the integrating of that. One gets the functional that needs to be maximized, and this is the so-called Ronkin function of that algebraic curve, also related to what's called Mahler measure in number theory. So this is a wonderful result by Kenyon, Okunkov, and Sheffield about 20 years ago. In particular, they could see the formation of these different phases of these smooth phases showing up using by looking at the behavior of the surface tension in particular. Now, that's great, yeah.
Wasn't the fact that the free energy comes from this function already known by Wolf in 1901?
In the general situation, that's fine, but computing the actual free energy for the dimer model, that's a different matter. I mean,
But even that was done in 1980.
For the general periodic dimer model?
Not general, no, not general, no, okay.
For which?
So that's what you're...
That's the contribution of Kenyon and Klinkov-Sheffield.
Exactly, yeah.
Yeah, they computed the free energy for an arbitrary periodic dimer model. Yeah. Yeah, there was a.
But for the square grid, I think Bernard was one of the contributors to that back in 1980 for the standard periodic one-by-one periodic case.
Sorry for not mentioning you. I'm sure you. Okay, I have to do my homework. I have to go back and actually look at the.
Well, you did already much more than anybody else so far in this meeting.
All right. There was actually another. So this work that I mentioned here. So it looked at the hexagonal lattice in the 3x3 periodic case. So that's the simplest case in the hexagonal setting when the smooth phase appears. And they got the free energy too, and they predicted the limit shape that will have, which is actually just the same as the shape of the free energy in the infinite volume, and they predicted they claimed the formation of the corresponding smooth phase and so on. And for mathematical tools, that remains out of questions for now, out of reach for now. So at least this is the first paper I know where the dimers got connected to this smoothness. Well, not this one, but to the smoothness thing. Okay, but I was getting to the point that once you have that functional, actually solving that variational problem for a particular domain is not an easy task. And I will mention Rick again, and this one, who is somewhere here, over there, who had a lot of progress recently in solving this variational problem. And I need to read their papers more to understand how they do it. And it's very recent progress, and it's wonderful. But still, it's not. I don't think it remains. It's become easy in the general setup. And so in this case, even if one gives the limit shape that I'm hiding from you, the formulas here in theta functions, can one actually check that this is the solution of a variational problem? Is it sufficient information to actually mathematically check that what I gave you is the limit shape? It shouldn't be bad, right? I mean, I have an explicit solution, there is an explicit variational problem, so what's going on? And that seems to have been achieved by Babenko, and Souris. The paper is not online yet, but there were talks. There was at least a talk by one of the Babenko in an earlier workshop here. It's also based on the work by Istvan and 3 other co-authors previously. So that path hopefully will give a verification argument that these algebraic geometric formulas actually give one a solution of the variational problem. Okay. Now, what we could do a bit more. So we don't just get from what we did the limit shape. The limit shape is fine, it's pretty, and it's visible on the pictures, and it's great. Now we can also go in the bulk and check the bulk limits. We can compute the correlations, and hopefully that should allow to compute various limits, local limits of the behavior of the dimers in different modes. So the bulk limit we were able to do, well, but more is to be done. And the rest, well, the last 10 minutes that I have, I want to spend, that's certainly not enough, but I want to tell you, so far I was sort of doing the show-offish so-called, look at these pretty pictures, we can describe them, wonderful. I want to tell you what goes in, what allows us to do it. Okay, what's the trick? There has to be a trick, right? So if you got lost or disinterested and want to jump in again, that's the moment. So here is an elementary problem. Take two 2x2 matrices. Okay, so here's a 2x2 matrix, here's a 2x2 matrix. There is a complex variable z here and here. So I view this as a matrix polynomial in z. A simple matrix polynomial in z of degree 1, with the highest term having rank 1, and another one in 1 over z. Now I will multiply these two matrices, and what I will want to do, I will want to write this product as a product of two other matrices in such a way that, so this matrix will have the eigenvalue. So the determinant of this matrix will vanish when z is equal to something. So I want that 0 in z to move to the left. And the determinant of this matrix will vanish when z is equal to something else. And so I want that 0 to move to the right. Of course, the determinant of the product doesn't care about the order of the factors, so the zeros in z will stay the same. I just want to swap them, right? Okay. And when you're in 2x2 matrices like that, well, you just do it. Okay, this is the formula. There is an x here that's a new thing, and that's just expressible in terms of the matrix elements. Right? That's all. And what do these matrices have to do with the Aztec? So just in one word, one can slice the Aztec, and then one can look at transfer matrices. If one represents the Aztec as a vertex model, so one can slice it and then look at the transfer matrices layer to layer. These will be some infinite matrices. They will be block tuplets because they're translational invariant on the layers. And so if you take Fourier transforms of those transfer matrices, then you get matrices like this. And so the geometry of the square lattice tells you that you need to, in order to build the Aztec, you need to, so this is a free fermion 6 vertex model. If one writes it in terms of dimers, you will have transfer matrices that will get alternated, two different types of them. In terms of random partitions, if you're familiar with the link, this will be adding a horizontal strip, a vertical strip, horizontal strip, a vertical strip, and so on. So these are two types of the Fourier transform transfer matrices between these layers. Now, what one wants to do in order to solve for the correlation. So the correlation, the problem of finding correlations, that's the problem of inverting the Castelline matrix. The Castelline matrix is big, so one can actually reduce it by the usual linear algebra to a much smaller matrix, which is really just the product of these transfer matrices across the diamond. And so one gets these two matrices, and then it's getting raised to a large power. Okay, just repeat them. And so then what one needs to do is one wants to move. So what will happen is that you will want to move sort of all z's to one side and all 1 over z's to the other side. So these factors will have zeros in z in different regions of the complex plane, inside the circle and outside the circle. And in order to invert the matrix, what one needs to do is to permute the factors in such a way that on the left, that your left factor will have all zeros inside the circle, and the right you'll have all zeros outside the circle. Right? So this is an instance of the Wiener-Hopf factorization of solving a Riemann-Hilbert problem that solves the problem of inverting the Castelline matrix for the Aztec. Okay. Okay. So I just packed a couple of hours of lectures in 5 minutes. I'm sorry about that. But I'm just trying to say that it's relevant for us to run this dynamics on matrices. So, you take two matrices, you flip them in this way. Oops. in this way. And then you take them by hand, you put them in the opposite order, and then you refactor. And you put them again and you refactor. And you want to do it 1,000,000 times. Okay? If you're able to do it, you won. Okay? This is a nonlinear map. Okay, it's not that complicated, but it's a nonlinear map. How do you iterate it? How do you describe the dynamics after 1,000,000 steps? That's what the trick is. That's what goes into the solution. Okay? And this is the fact, okay, never mind.
So,
yeah.
Is that formula always subtraction free? Do you ever get a minus sign somewhere in the
It depends on which matrices you look at, but for the matrices that come up here, you don't. I mean, these are actually formulas from, the matrices you get here and the permutation thing is from the work of Lemon-Pilavsky that you would know well from 15 years ago, something like that. Yes, yeah, they are subtraction free. Yeah.
This looks very similar to what happens with cluster algebra, in which you can often reformulate things in terms of refactorization dynamics. So, is there any?
So refactorization dynamics is everywhere.
Right.
This refactorization dynamics here is equivalent to the shuffling, which also has on a torus a connection to the cluster algebras through the work of Rick with Goncharov. So yes, it's close, but can I meaningfully use it here? No. I can use it. The proof uses the spectral transform that's accessible through the work of Rick with Goncharov, and so it's useful. But can I put cluster algebras in this picture and say, oh, look, I used them for a good reason? I can't do it. Maybe you can. Anything else? All right. So I'm down to my last 5 minutes and to the problem of iterating this matrix refactorization 1,000,000 times. Okay. So the trick there. This is a very well-known topic in integrable systems. It goes back to mid-70s under the name of the finite gap method. Okay? And we were just lucky to know about the existence of that method. Okay? So adapting it is a little bit of work, but the method is really there, has been there for a while, but it's from a different field. So if I multiply my two matrices, so this one and this one, I get this matrix that I call P of Z, and you see it's a polynomial now of degree 2 in Z. And what I'm trying to do, instead of P minus and P plus, I'm trying to write it as P, well, I first flip these two, I get P plus and P minus, and then I refactor it. And that's my dynamics. Okay. So the trick is that this dynamics becomes linear if one looks at the eigenvector. Okay, so when I do this flipping, the determinant of this matrix is not going to change because the flipping is a conjugation operation. Not only the determinant is going to change, the characteristic polynomial is not going to change. So the characteristic polynomial actually collects all integrals of motion of this dynamics in terms of integrable systems. And if you look at the set where the characteristic polynomial is 0, that's my spectral curve. That's the Riemann surface that showed up. And when the determinant, the characteristic polynomial is 0, that means that there is a null vector, right? The matrix must have a null vector. So that null vector is the hero. It's called the Baker-Akiezer function in the integrable systems literature. And so if you look at that null vector and you see how it evolves, that solves the problem. Now, the reason for that is that that null vector will be a function. So this is my, the determinant of this is the characteristic polynomial. This is my null vector. It depends on z and w. Z is the variable here. W is the proportional thing to the identity that I'm subtracting, right? So this is the eigenvalue over here. You can think of C's as being eigenvectors and W's as being eigenvalues. So then you get a function in Z and W, a vector-valued function in Z and W. It's a meromorphic function on your surface. It's a meromorphic function whenever this has a solution, on the set where this has a solution, which is the spectral curve. And meromorphic functions are wonderful because you can describe them by zeros and poles. Okay. And so if you watch the behavior of those zeros and poles, then the flow on them becomes linear. That's the wonderful discovery that in some case goes to Baker, which is late 19th century, and then Achiezer we discovered in the 60s, and then in the 70s there was a large activity, a breakthrough of activity in the 70s by Novikov and his students, Dubrovin, Krichever, and there was also in St. Petersburg part there. And it's really quite known under the, so it's applicable. So it's applicable to the KDV solution in particular. So this is over here, right? So, well, okay. I didn't tell you. I skipped a part. I told you that zeros and poles are nice. Well, zeros and poles, they still live on your Riemann surface. They still live in your algebraic curve. So it's not quite clear what does it mean that their flow becomes linear. Well, to make it linear, they need to be sent to the Jacobian of the curve. So that's an object that's well known in classical complex analysis. That's a torus. So if you have a Riemann surface, there is always a torus that one can associate to it. Pretty much when you integrate canonical basis of differential forms, you have periods in two directions. And so those periods will give you a torus somewhere down the road. And so once you send the zeros and the poles to that torus, then on that torus there will be a linear motion which literally explains what your dynamics is doing. So there is this transformation that sends your nonlinear system to a linear one, and so then you can solve it. Everyone can travel down the straight line. Now, okay, that's another 2 lectures in 5 minutes, and apologies for that as well. Okay, never mind. Okay, so this is just an example of where this refactorization dynamics shows up. Okay, so this refactorization of matrices, right? It's got to be quite fundamental because everyone multiplies matrices, right? So cluster algebra is certainly one case, but there are other cases. So something known as QR algorithms for finding eigenvalues of matrices. If you have a matrix and you need to numerically find eigenvalues, if they're real, one can do QR decomposition, then flips the factors, then QR decomposes, flips the factors, and so on. If you run it for a while, you get the matrix to what's called the Schur form, and so on the diagonal, you get the eigenvalues. That's literally used millions of times. It's a fast converging algorithm in linear algebra. Now, why Jacobi introduced, okay, I wasn't near Jacobi at the time, but why Jacobi introduced theta functions? So one of the problems he was solving, he was looking at geodesics on ellipsoids. Okay, so those are expressible in terms of theta functions. Now that system, looking for geodesics on the ellipsoid, actually that's a special case of looking at billiards in an ellipsoid. So billiards in an ellipsoid is reformulatable in terms of a matrix factorization dynamics. It can be integrated just in the same way. The relevant curve is the torus. And so when one goes into the formulas that move you from the torus to the Jacobian, which is also a torus, one gets theta functions, and that's how Jacobi needed theta functions. And okay, so the last one is some discretization of the earlier equation of the rigid body motion. So that was also one of the early topics in integrable systems. And Kovalevskaya work in particular, and find in different cases when you can solve the rotation of the solid body. I couldn't resist. I never worked with pictures, so when I needed to do a summary, I just put the pictures out there. I'm not sure I'll ever be able to do that, but for once I had fun. All right, thank you very much for listening.